I am so excited to release your assignment to stage 1. Yeah, this will be stage 1. There's going to be a stage 2. Stage 1 is going to be a fantastic learning process. Stage 2 is going to be a learning process too, which is going to be less technical and more like trying to figure out how to find parts and actually put a good report together. So stage 1's all about like the meat and potatoes of actually designing a control circuit for a DC motor. We are going to talk about speed control or power control, and we're also going to talk about directional control. Yeah, we're also going to talk about like how to turn it on and off, because that's important too. Okay, so let's go. I made this awesome PowerPoint and let's go through it. So DC motor control, welcome. And by the way, DC motor control is completely different than AC motor control. What? Really? AC motor control is actually really fascinating. AC motor control is controlled by the speed of an AC motor is controlled by the frequency. Yeah, you just change the frequency and its speed changes. You can kind of change the speed by giving it different voltages, but it's nowhere near as efficient. It's just not designed to do that. So if you put a dimmer on your grinder, it kind of works. Slows it down, but doesn't really, there's no power in it anymore. Let's go on. Okay, here we go. So this is what we're going to do. We're going to talk about DC motor power and what that actually means. Like, what does it mean if a motor has DC power? We're going to talk about the definition of DC motor, and we're going to look into calculating it. Yeah, and how do you actually calculate it? And we're going to look at some data sheets. It's pretty complication calculation, actually. You'll be surprised about that. Okay, good. And we're going to look at DC power control, and we're going to find something really fascinating about voltage and current, and it's actually proportional to the square of the current and the voltage, actually, which you know, because you know the formula. Anyway, so we're going to look at methods of DC power control, kind of 2 different kinds of methods. We'll take a look at that. It'll be pretty cool. And then we're going to look at reverse circuits. There are lots of different kinds of reverse circuits, and they're so cool. Yeah. So yeah, you might not have thought like, oh yeah, you can make a DC motor go backwards. Yeah, just flip the polarity. It's pretty awesome. And we'll also look at safety considerations. Yeah, something called an interlock. Yeah, interlocks are really cool. Good. And then we'll look at fuse selection, pretty simple. And then we'll actually look at some design and kind of how we actually put all the different designs together. We'll look at all these different kinds of designs. So let's jump into it and talk about power. Like, but what is motor power anyway? What's DC motor power anyway? So a motor's power is how much work it's doing over time. Okay, so work is like just energy. So when a motor is rated, say, for like 100 watts, it doesn't mean that it's converting 100 joules of energy every second. It's rated for 100 watts. Doesn't mean that it's actually, dealing with 100 joules. It's not doing that much work every second. Motor specification of 100 watts indicates that it's capable of doing 100 joules of second, 100 joules of work every second, but it doesn't specifically mean that it's actually doing it at that time. So factors affecting DC power, power, not just speed, but power, actually are the load it's driving. Yeah, the load it's driving, obviously, if it's lifting a weight and there's a certain amount of energy in the lifting of the weight, that's gotta like somehow factor into what the power of the motor is. Yeah, and actually, this is crazy, but the resistance of a motor changes. And you've studied this. Actually, you studied this in one of the labs where you actually put your finger on the shaft of the motor and you changed it. You saw the current go up. Well, that's crazy. How did the current go up? Because the resistance changed. The dynamic resistance of the motor changed. Well, I said that like trippy. Because it's so important. It's so cool that actually happens. And the power of the motor is related to the voltage across the motor. So if I want a motor to be more powerful, I just kick the voltage up. Yeah, and then the power increases for sure. And we'll notice that there's a cool trend to that. And the resistance of the motor winding itself. And then the current through the motor as well. Okay, so let's take a look at this. Now, these are 2 loads here. Now, this might jump out you at first. You might kind of scratch your head. So, wait a second. Okay, one weight is heavier than the other. Okay, and what's going on here is that the bigger weight, which is obviously bigger, the motor is doing 72 watts. So that gray thing over there is the gearbox. So there's this motor, it's spinning really fast. It's spinning like, I don't know, like 2,400 RPM. And the actual gearbox kicks that down to like, I don't know, like 112 RPM, something like that. Anyway, slows it down quite a bit. So it can lift this heavy weight, and it increases the torque of the motor. That's a whole other thing. You'll study that later. Okay, so let's continue on. But why is the heavier weight, which is heavier, so if I were to lift that weight from here to there, well, that's more joules than lifting the other weight, which is smaller from here to there. So wait a second. There's more energy being used to lift that weight. Well, how come this is only 72 watts and this is 90 watts? Well, there are actually lots of different reasons to that. To unpack like the whole wattage of a motor, again, remember, it's the energy per unit time that's actually being used by the motor, or the energy is coming from the voltage, right? From that push. So how much of that, the energy ultimately is coming from the power source. Whatever, it's a battery or whatever it is, that energy is coming from there. So how much energy is it, like the motor is pulling from that power source to lift these weights? So what's going on is that the current changes depending on the weight of the load, and you've seen that because when you grab it, there's more current for this more weight. So obviously this guy down here is actually drawing more current. Okay, so if he's drawing more current, how come there's less power? Well, power is a function of energy over time, right? We know that. So that's like a big deal. So what exactly does it mean that one application is more powerful than the other? Well, power means the energy is used over the same time. So what exactly does more energy mean? Well, in this case, there are two different weights lifted to the same height. So different amounts of energy are being used, for sure. So we're just assuming, it doesn't say that in the diagram, but we're saying that these weights are lifted to the same height. Okay, well, that's fine. They're lifted from the floor up to the table or wherever. But why is a lighter weight showing more power? Well, there are several factors that play into this. And one of the factors is time. Yeah, time. Really important. So what's going on essentially is that this motor is, because this weight is heavier, it's actually struggling a little bit to lift the weight. So it's taking more time to lift it. So if I have more energy, that's actually, in the end, this weight goes from here to here, the more energy is used to lift the weight, but it takes a lot longer, well, then the power is actually less. Yeah. So it powers energy per unit time. So that's actually what's going on. We have to understand that. Plus, look at this. This is complicated. Dude, there are a lot of different charts like this for motor characteristics, motor power characteristics. So let's just take a look at it, or more specifically, motor performance. So because it has power on it, a bunch of other things. Look at this, efficiency. Oh, there's this like sweet spot for efficiency. Yeah. So choosing the right motor to do the job is actually really important. So you have to like look at the mechanism and the job itself, and you just say, okay, I have to make a car accelerate around a corner or up a hill or go down, or I have to make some machine lift something or pull something or push something or whatever, or turn a hydraulic motor or turn a hydraulic pump or something. You've got to look at the mechanical needs of that motor and what's actually going on. And power is a big part of that. And then from there, you have to like look at the voltage and the current and a whole bunch of stuff. It's pretty complicated, but really in the end, it's just practice. But what's going on here is that you have to actually you have to go and select the right motor so that it works into your application, so that it fits into this efficiency range. It's pretty cool. So look at this. So now wait a second. There's this curve here that's going on, and this blue curve down here, it shows us the torque and the current. Okay. So wait a second. We have seen that when you stress the motor, the current goes up. Okay, so we stress the motor, the current goes up. Okay, that's fine. So what's happening is that this heavy weight is actually demanding a higher amount of current because it's down here. So the current is over here. So the power is actually going to be less. Now over here in the efficiency range, this is closer to the efficiency range. The lighter weight is over here. And what's going on is that the power is actually higher. Yeah, it's actually higher because it's actually using less current. It's actually moving faster as well. So it's just a more efficient process. So essentially what's going on is that motor, whoever selected the motor, it's not actually selected, but the motor wasn't actually selected right. So it's actually stressing to lift the heavier weight. So the lighter weight, it's fine, but it's a 100-watt motor, so it's okay. It's just that when it's lifting the heavier weight, it's not maybe as efficient as it could be. Okay, so that's what's going on. And we understand that time is a big part of that. So voltage, let's just unpack voltage and see what's going on. So is it possible to make the same motor lift a heavy weight as quickly as the lighter weight? Well, yeah. So they would actually be, that would mean that motor would actually, this is cool, that motor would actually be producing more power than, the same motor would be producing more power lifting the heavier weight than the lighter weight. But if we kick the voltage up, well, how much would we have to kick it up? Well, that actually depends on a lot, but it's a really basic formula, and it actually boils down, well, the root of it is a basic formula that boils into power. So let's take a look at the formula for power. So this opens up some questions. What's the voltage range of the motor? Oh, yeah. Right, because I can't push that motor too much. So if I had like a 100 watt motor and it was like a 24 volt motor, could I run it on 6 volts? Well, yeah, it would just go slower. Could I run it on 24? Well, yeah. So how much voltage can it handle? Like what's it required, and how do I determine that? A lot of really good questions. So take a look at this. The voltage recommended by the manufacturer is not necessarily the voltage that will be applied to the motor during operation. Not specifically. I mean, it's just a recommended value. If there's very little to no load, you can actually kick the voltage up. You can pretty much double the voltage. You're not actually damaging the motor. Make it a little bit warmer than it likes, and the bearings are actually designed for a certain speed and all that. So you don't want to like double the voltage of the motor for very long, even if there's no load. But the thing is, you can do it. It's not going to blow up. It's going to be okay. But if there's a load on it and you do that, it'll blow up pretty quick. Yeah, it does not like that. So it all depends on the load and how much you're loading it. If you actually want to overpower it, or if you want to over voltage it, I guess is the right thing, which is actually kind of overpowering it as well. So the rated value for that understands that, you know, if it's a 100 watt motor, it's designed to do a certain amount of work. Certain amount of energy. It's supposed to be able to, you know, transfer a certain amount of mechanical energy per unit time, or do that much work. And if it's doing that, then do it at the voltage it was designed for. Don't kick it over that. But you know what? Again, if it's no load, and if the load is very light, yeah, you can kick the voltage up. And if you want, again, we can turn the voltage down to actually lower the power of the motor. But what's going on there is that voltage, yeah, look at that. That's the squared. And we know that. I mean, that formula it's not surprising. But there's not a linear relationship between voltage and power. And we can see that. And that's pretty cool. So what's going on here? I just have this circuit here where I'm like, okay, so if I were to vary this, is it okay? Can I double this voltage? What can I do with it? Well, that's okay. Therefore, doubling the voltage increase the motor power significantly. Yeah, like a lot, because it's squared. So we have to kind of be careful about the voltage, how much we overpower this voltage. But again, the power, okay, let me say that differently. How much we overload the voltage, or over increase the voltage. That's way better. Over increase the voltage. We have to watch how much we do that, because if we actually increase the voltage just a little bit, it increases the power quite a bit. So again, power is completely related to the load itself. So the voltage and the load are really, really very connected, or the the power, the load on the actual motor itself. Again, if you're doing a load and it's actually doing, if it's a 100 watt motor and it's actually doing 100 watts, so mechanically it's doing 100 joules of energy. It's transferring 100 joules of energy per second. Stick with the voltage for the motor. Don't increase it. But if the load is lighter, you can increase the voltage, so it's okay. There you go. So, but don't overspeed it. Don't make it go really, really fast, because the bearings will blow out. Okay, so example, here we go. So when 24 volts is applied to DC motor with a dynamic resistance, okay, so that's interesting, the dynamic resistance. What does it mean? Well, you've seen that in play in the lab. When you physically put your finger on the motor and you slowed it down, you saw the current went up. Therefore, the resistance changes. But wait a second. How can the resistance of a motor change? It's the same motor. Well, again, the resistance is dependent on the load. So therefore, the power is dependent on the load. The load is a huge part of what's going on with the motor. If you don't consider the motor, the motor load in selecting the motor, you're just something's going to blow up. Okay, so yeah, it can change the resistance, and that gets into magnetism and back EMF. So go watch that video on back EMF or Lenz's law. Yeah, big time. Go watch the video on Lenz's law. Actually, listening to me talk about this right now, and then watching that video on Lenz's law, you're gonna do the click, click, click. Wow, motors are so cool. Yeah. Okay, let's continue on. Okay, the operator wants to lower the motor's the motor's power to 50% or 50 watts. Okay, so what's the voltage that we need to apply to make that happen? So let's say we're running this motor and it's running at a particular wattage because it has a certain load on it. And while it has that load and while it's running, the resistance is this. So the problem is actually when we slow it down or speed it up, the resistance changes. You see me scratching my head? It gets complicated. But we're just going to roll with this for now. Just kind of like, we'll just kind of say that it's linear because it's a ballpark kind of feeling. It's a ballpark thing. Often we want to kind of just play with the adjustment. But let's do our ballpark adjustment. And we're going to use this formula. Oh, look, I put subscripts and stuff in my formulation. Yeah. Okay, so applying the voltage power of 80 watts into the formula gives us a voltage of 17 volts. Okay, that's fine. So if I needed this 80 watts and I plug the numbers in, I'd need 17 volts. Okay, so that's cool. So 100 watts at 24 volts, 80 watts at 17 volts. It's not linear. Let's take a look at this. What's going on again? Here's this formula again. I don't know why I said 50 watts, but I calculated 80. Something happened. Okay, so let's just continue on, but you get the concept. Okay, here we go. And you see the formula. So we've learned that the power characteristics of a motor is not specifically the rating, but it's dependent on a whole bunch of things. It's dependent on the load on the motor. See, that's on the top. Oh, that's interesting. The motor selected itself, the voltage applied to the motor, the speed and torque, and many more things. And as you can see, the motor performance characteristics are like complicated here, and there are lots of other charts that look like this. I have another one actually coming up. Okay, we also learned that the selection of a motor for any application requires a detailed analysis of the application. Oh, absolutely. Oh, there's more stuff. Oh, DC power control. Okay, let's talk about how to actually control the power. And we have seen through one example and basically through the formula power is V squared over R, we can see that if I wanted to change the power and I wanted to do that by applying different voltage, well, we can see it's not linear. Well, there's a graph here, and that's fine. So this voltage goes up here, and that's what the power looks like. Okay, that's fine. I just put this together so you can see that it's not linear. It goes up like this. There's your formula. And note, due to the complexities of the motor characteristics, this voltage-power relationship is only loosely applicable. It's kind of a ballpark. It's a good place to start. Okay. So for estimating the power of a motor with a specific applied voltage. Okay, so the voltage power relationship is affected by many other factors such as the motor application, RPM, current, and changing resistance of the motor. It's a big deal. So the voltage versus power relationship is a good place to start. We just kind of like, we'll just see if I turn the voltage, because that's how you control the power of a DC motor. Because as far as control circuits go, that's what we do, because we can't actually control the current. You can kind of limit the current with a rheostat, but ultimately you're just really controlling the voltage drop. And that's what we're going to actually look at in the power control. It's not going so much a rheostat, but we're controlling the power of the motor by actually putting a resistor in series with it to steal some of the voltage from the source. It's not an efficient way to do it, but ultimately it's voltage control. The speed and power of a motor is controlled by voltage. Okay, that's pretty much what it is. Okay, so we've seen that the voltage power relationship is complicated, but leaving details aside, how do we control the voltage of a motor? Like, how do you do that? Well, essentially there are two ways to do it. One way is with pulse width modulation, and that's actually the most common way that it's done, and it's pretty cool. What's going on is, just imagine my finger is the voltage, okay, graph. So the voltage goes up and the motor comes on, and then all of a sudden, like milliseconds later, the voltage goes boop and disappears. Back to zero again, but the motor's still spinning, right? Because you got it going. And then the voltage goes up again and then down, up and up. So it kind of pulses, kind of teases it. It's kind of like if you're rolling a tire down the road, right? And you push it every kind of like 10 turns. it'll go. But if you run after it and kick it really, really hard, it'll go faster, faster, faster. That's pulse width modulation. And it's really simple to do with electronics. You can even do with a relay, but the thing is, pulse width modulation really goes really quickly. And you can't actually control it that fast with a relay. So we use a solid state relay or other kinds of integrated circuits. So you guys will talk about that when you get into Mechatronics 1 if you're going to take that course. If not, just remember that pulse width modulation is pretty much the main way to control a DC motor. But what we're going to do is we're going to do like a simple, kind of more down-to-earth approach. It's wasteful and it's not as accurate, but it works and it's cheaper, or maybe not cheaper. It's just simpler. Let's just roll with it, okay? The other thing is an inline resistor control. Essentially, all we're doing is replacing a resistor in series with the motor. We're just stealing some of the voltage energy. Like, let's just go back to power again. I'm kidding. Wait, let me just talk about this. You know that the reason there's a voltage drop across a resistor is because the resistor itself steals voltage, producing heat. And the voltage, of course, the reason it's stealing the voltage is, it's not really stealing voltage, it's stealing energy from the voltage. And voltage is, energy per unit charge. So as the charge is kind of being pushed through the resistor, energy is used to push it through, and then heat is created and all that. So I just keep saying energy, and we know that power, because we're studying how to change the power of a motor. So power is all linked to energy because it's energy per unit time. So wait a second. If we take some of the energy from the battery, because it's in there, or the power source, whatever that power source is, it could be from a motor or whatever. It could be from a generator, from a diesel generator, whatever. There's energy in the fuel, and it's being changed to mechanical energy, and that's being changed to electrical energy, and the electrical energy comes out in the form of voltage per unit coulomb, and then one of the batteries that's in series steals some of it. So the motor gets less. That's what's going on. That's how we can control the power of a motor. Just steal some of the energy. And we do that with an inline resistor. So we have looked at this before. You guys are experts at that circuit. You know how this works. You get it. You get a selector switch. I flip it to one resistor, the next, the next, the next, and the resistors get a little bit smaller and smaller and smaller and smaller so that they steal less of the energy. And then the final selection, selection 4, there's no resistor and there's no energy that's stolen at all. So, okay, that makes sense. But if we wanted to accurately control the power to the motor, let's just say we wanted to do that, which we do. So we want to say, okay, the first switch puts the motor at 25% power. Okay. So, and then the second one goes to more and more and more milliwatts, 100 position, milliwatts, 100 watts. I think I did this wrong. Oh, sorry. In this circuit, it goes from fast to slow. Okay, that's cool. So it goes from fast to slow. So what's going on here is the motor's resistance is 100 ohm, or the dynamic resistance, and we know that's going to change. It's okay. Just ignore that. Okay, here we go. So the motor's resistance is 100 ohms at position 1. Okay, so at position 1, there's no other resistance anywhere, and the motor is only 100 ohms. So the motor's actually seeing 12 volts. That's fine. At position 2, we get 1,000 milliwatts, and then 850, and then 500. That's fine. Oh, that's fine. So remember, the voltage-power relationship is an estimate. Okay, that's fine. It's just an estimate. We're going to work with that, but let's just continue on. Now, in this case, if we want this resistor, so this is another situation. This is a different circuit. In this case, we're going to slow the motor down. Okay, good. So we're slowing the motor down. So position 1 is the slowest. Or no, we're going to speed it up. As we rotate it to the right, we'll speed it up. Position 1 is the slowest, and then from there it goes more and more and more. So wait a second. So we know that the motor is 24 watts. We want to calculate what the total power of the motor is, and we're assuming there's a load on it. The reason we know there's a load on it is because the resistance is 6 ohms. And again, the resistance would change if the load changes, but we're just going to keep the same load on it. Okay, good. So if I put the switch to all the way to number 4, what's the power of the motor at full power? Well, that's easy to calculate. So I'm just going to calculate this. I don't know if you guys notice this, but there's a bracket here. And that bracket is, just bear with me for a second. We got to do some math. This bracket indicates that the 2 is squaring the voltage and the number. Because, you know what, we have to square the unit because you have to do the math with the units. By the way, a watt is a volt squared per ohm. That's weird. Does that mean a joule per second equals a volt squared ohm? Yeah, pretty cool, eh? Yeah. Okay, so let's continue on. So we can see that the calculation is done this way because the brackets here and the brackets there. Put your brackets in there because you know I'm just going to, if you don't put those brackets in there, you're going to get 0 for all of your calculations. Well, I'm so mean about that. Okay, so yeah, put your brackets in because it applies to both. And 24 watts, okay, that's cool. So 24 watts. Now, we know that's 24 watts. Now, I want to find the voltage across the motor so that it runs at 80%. Okay, so I know that at 12 volts, it's 24 watts. 80% of 24 watts is, 24 watts is 24, doesn't matter what it is. So I just multiplying it in here. So here's my formulation. So I'm going to write my formula down. I'm rearranging and I got all my subscripts in and I'm rearranging. So I'm just, that's the power formula. Okay, so I'm solving it for voltage. Now, if I applied 10.73 volts to that motor, then it would be running at 80% power. Okay, so I know that. But wait a second. I know that at switch 3, I know it's 80% power. So wait a second. I need this thing to have 10.73 volts and my battery is 24 volts. So I need to put a resistor in here that steals actually quite a bit of voltage. Well, let's take a look. How do I calculate that? Well, there are lots of different ways to calculate it. One is I could do Kirchhoff's voltage law for a circuit, and then that would give me the voltage drop across that resistor. But I don't have the value of the resistor, and I have the voltage drop across it. But Ohm's law tells me I need the current too. So, okay, there's another step there where I could solve the current. Well, how do I find the current through the motor? I could use the power rule. Yeah, I could use another, because remember P squared is equal, P is I squared times R. You know, I could use that. Okay, so there's 2 steps here. And that calculation's another square root. I better keep these numbers in my calculator. So that calculation is another square root. So I can find the current going through R3 and the motor, because they're in series, by just knowing the power of the motor and knowing the resistance of the motor, and then I could calculate the current through the motor, and then I would know the current through R3. I know the voltage drop across R3 because Kirchhoff's current voltage law for a series circuit tells me the voltage drop across R3 plus the voltage drop across the motor is going to be 24 volts, and I know the voltage drop across the motor. Okay, that's like a 3-step process, because from there, then I have to, that's a 2-step process. I have to calculate the power, the current. 3-step. I have to calculate the current, then the voltage with Kirchhoff's current voltage law, and then using Ohm's law, I have to calculate the resistance. So guess what? The power of the voltage divider. Yeah, it comes in. It's powerful. So what I've done here is I've taken the voltage divider, which we're familiar with, the voltage drop across the motor, by the way, which we know. Okay, is the voltage source, which we know, and then the voltage of the motor we know, and RT, well, we don't know it, but we can rewrite it. Is RT is MT plus R3. By the way, you don't need to remember this derivation of this formula. I'm just walking you through it because it's pretty cool. So let's continue. Okay, so here I have this formula, and then I'm going to rewrite this. I'm going to cross multiply and put this over here and do this. So now I have MRM plus R3 equals VS times R over M. Now I look at this. I got 2 voltages. Well, here's that theme coming in again, where you have some value multiplied by some ratio of some things. Before we had current multiplied by a ratio of resistances. And also that was for the current divider rule. For the voltage divider rule, we have some voltage divided by 2 resistances. In this, we've seen that voltage is actually the ratio itself, and that's multiplied by some resistance. That's pretty cool. Anyway, that's just another kind of theme that I'm seeing pop in, which you'll see in electronics all over the place. Anyway, here we go. Now, I can solve this formula for R3 quite easily. Oh, look at that. I get this nice, clean, simple formula to calculate the resistance that I need to control the power of that motor. And it's just that simple. It's pretty cool. So I can do this in one formula as opposed to 3 steps. Nice and clean. Always use as clean as you can calculations when you're presenting your work. Because, dude, someone else, the reason you present your work to somebody is so someone else can be empowered by it. That's it. I need you to understand that. The reason you're doing this work is not to give it to me so I can mark it. That's not it. You're practicing how to build a document, how to build a report, or how to build to have a method to put together so that you can document this information so you can share it with people and you know what, and work in a team or build it yourself. And like 5 years down the road, dude, sometimes when I build stuff, I do some calculations or something, and then I go back and I look and I'm like, what did I do? What is this for? Why did I do that? I always make notes, always make headings on your formulations. Because when you go back years later, you'd be like, what does this mean? Yeah. So here we go. Using that nice simple formula, that one-step formula, I can easily calculate the value of R3 so that it will make my motor run at 80 watts. And you just do the math. So, oh, really? 708 milliohms? Actually, yeah, you're going to find that you're going to have some values that are really low. And we're dealing with a motor that has a really low resistance as well. So you're going to end up with resistance that are really low here. Okay, so what we're going to do now is we're going to calculate this resistor here. So what we're looking at is we want this thing to run at half power. So did we divide the voltage by half? Well, no. We've seen that it's not a linear relationship. So let's just do the math. What is the voltage if I put on this motor to make it run at 50%? Well, just unpack this formula here, because this is the power formula with voltage in it. I put my values in and 8.49 volts. Okay, that's cool. 8.49 volts. I can deal with that, and I'm just going to say, okay, so what do I do to make that happen? And as I'm looking at this right now, I realize this is labeled wrong. That says 24 volts, but here I put in 12, and that's much better. So if you caught that, that's good. If you didn't catch it, you're not paying attention. Anyway, it looks like I wasn't paying attention either when I made this. But so just imagine that says 12 volts. What does that say there? Oh, that says 12 volts, right? Yeah, it does. Okay, so let's just pretend it says 12 volts and then move forward, because then everything will work if we just do that. Okay, good. So if I ran this motor on 8.49 volts, then it would be running at 50%. Okay, that's cool. So we have a 12 volt source. And you'd think if I kicked it down to like 6 volts, then the motor would be at half power. Well, no. I kick it down somewhere in between 12 volts and 6 volts to actually make it half power, because it's not a linear relationship. Okay, so now what resistor do I choose for R2 so that my motor is going to run at 50%, or more specifically, so that it's going to get 8.49 volts? Well, we know that there's this cool formula. Yeah. So just fill in the formula, put my 12 volts here, and I do a thing, and that says 2.48 volts, 2.48 ohms. Okay, so if this guy is 2.48 ohms, and I put this switch here, it takes this 12 volts, and it divides it up, and the motor is going to get 8.45 volts, and this guy is going to get 2.48 volts. Okay, good. Well, there you go. So now our last selection, R1, the way we do that is we're going to say, okay, what's the power at R1? It's 25%. Okay, so again, all we need to do is calculate the voltage that I need to apply to that motor if I want it to run at 25%. And we're going to see that it's 6 volts. Do you understand how cool that is? Okay, can you see this? You read that? See how that said 12 volts right there? Yeah, sure. So it's 12 volts. Okay, so what's going on is that if I half the voltage, the power of the motor goes down to 25%. It goes down to a fourth. Oh yeah, because 1/2 squared is 1/4. Yeah, see, it's just the squared, so it's the square of the voltage. So it's nice and eloquent. I've said that word twice now, but I think it is. Okay, so there you go. So now you know the 3 values of resistors. Now, for your assignment, you're going to have to choose these 3 values. You just have to go through this, process. And you're going to label you are going to label actually the assignment actually runs on 24 volts. Okay, so whatever, let's just continue on. So in this case, yeah, 6 ohms. Oh, is it the double slide? Oh, I think I just backed up. Okay, so now here we go. So position 1 is 25% power. Now position 2 is 50. Position 3 is 80. And then position 4 is 400. And I've labeled all my values. Sweet. Okay, great. Well, oh, there's more. Yeah, reverse control. Oh, yeah, we have to add another level of control to the motor. Yeah, how do you make a motor go in reverse? Oh, yeah, really? Is it simple? Yeah, so if I have a DC motor, I just flip the polarity, just flip it over. Yeah, and it just goes the other way around. It's that simple. Okay, so we're done. No, actually, how do you make a circuit that does that? Like, what do I do? Run over and unwire it and then wire it back over again? I remember I was driving across the prairie once, and my buddy's old car, 66 Chrysler 300, the switches didn't work for the power windows. So we I remember ripping the wires out of the switches because they didn't work, and I had to figure out some crazy way to put the wires together to make the motors go up and down and stuff, and it was pretty crazy. But yeah, you just have to flip the polarity on it. Anyway, and we were driving in the prairie, dude. We had to open the windows. Okay, good. So what do we do? Well, we have to add on-off control. I mean, it's just the first thing. I have to kind of mention this, because no matter what, if you don't put on-off control into your motor, reverse is fine. Forward's good too. But on and off is actually more important. Okay, good. So just make sure you put on and off control in. A single pole, single throw switch is one way to do it. There are lots of other ways. Actually, you know what? We have it here. Just flip the motor all the way to the left. Flip the switch all the way to the left. Anyway, here we go. So let's take a look at this. Look at these different options. Okay, so the polarity control. There are several circuit configurations and different components that we can use. Circuit types are H-bridge, double pole, double throw switch configuration, and there are other kinds. There is actually a double pole, triple throw switch configuration we'll look at as well. And relay. Oh yeah, you can do it with relays. Yeah, you can. So there are actually more as well, but we're just going to unpack these. Anything you can think of. That's great. I love it. Actually, I have a cool challenge of I'll post it. I have a cool challenge of actually how to do it with just one relay. It's pretty cool. Okay, so yeah, H-bridge, it's more of a configuration, and I'll show it to you. It's something that's not actually standard. It's not really done. This is kind of something that I kind of did in the prairie when I was with my buddy, and we just had to get the windows open. Actually, we had to make switches out of paper clips and stuff. But we did it. But you had to be really careful because you would short it out if you did the switches. So essentially, this is not a real control circuit. It's kind of the basis to understanding an H-bridge. So if you wanted, you could build a control circuit like this. You'd have to be mindful though, because you can't close switch 1 and switch 4. If you did it, it would short. If you close switch 2 and switch 3 at the same time, it will short as well. So you have to be really careful. You have to close switch 1 and then close switch 3, and it'll go in one direction. If you want it to go in the other direction, you have to open both switches. Oh yeah, in this case, we don't actually need an on-off because they're all of these. I mean, if I open all of them, the thing's going to go off anyway. So if I wanted to turn it around, I would open switch 1 and open switch 3, and then I would close switch 2 and close switch 4, and that's fine. It would turn around and it would be fine. But it's not a real control circuit, but you can do it. But it's the basis for what we call an H-bridge. And an H-bridge is the most common way that a circuit, the direction of a motor, a DC motor, is controlled. But more specifically, it's solid state. Yeah, when you go buy an H-bridge, it's solid state. So, and that's cool. It's got brains in it. So yeah, because the solid state actually knows not to turn switch 1 and switch 4 on. Because it's like an integrated circuit. It knows. So it can do that. But again, you could actually build, if you didn't have the switches and you just needed to make this happen, then you could do this. You just have to be really careful to control it. Okay, good. So this is another way. If you have this type of switch, I'm saying switch singular, even though it says switch 1 and switch 2. I've got this labeled as switch 1 and switch 2 to kind of show you that actually you need 2 of these, although because it's dotted like that, it's actually mechanically connected. So if you look at this switch, we can see that there are these 3 connections here, and then there are 3 connections on the other side as well. So essentially, the switches are mechanically connected, but you can see electrically they're separated. So what's going on here is that If the switch is up here, the current goes this way. Watch this. It goes through the motor, it gets to here, and then it goes back to the battery. Okay, so if I turn the switch the other way, both of them change because they're mechanically connected. Now the current goes from here into here, it goes to the motor, it goes up here, down here, around there, and then it goes through there because that's down as well. It goes back to the motor. But in this case, you need to add the single pole, single throw switch because the control is really important because you have to turn it off. Because if you put it on your go-kart or something or your car, it's kind of good to have the ability to stop. Yeah, that's cool. So there's another way to do this. This is pretty cool. So in this particular situation, you don't need the single pole, single throw switch. So this switch is more expensive, but the single pole, single throw switch is pretty expensive too. So adding it in, so you might as well just go buy one of these if you're going to build a circuit. But you can do this if for some reason you want some kind of like override or something, or maybe you want an extra override. Maybe you want to even put this type of switch in here as well. So you have two methods to turn the system off. What's going on here? This is a double pole, triple throw switch. It's pretty cool. So the one in the middle is a blind connection. You can actually, in this case, it's considered a blind connection because it's not hooked up. But you can hook it up if you want. But you see it's labeled 0 in the middle. So what's going on is that this connection here is, this is the center power. That's the center power coming in here. And if you flip it one way, it goes to there. And if you flip it the other way, it goes to there. Actually, the blind connection is fully blind in here. It's not connected to anything. You can't actually connect to it. But you can get one of these where you can connect to the middle. But it doesn't matter. As far as you look at it here, that's the center pole. And if you flip it one way, now watch this mechanically, just to let you know. If I were to flip this switch to the right, what happens is that means that this pin and this pin get connected. Yeah, it's kind of not intuitive. And you can, but the thing is, the important part here is that if you put it in the middle, it stays there, it stops. It can toggle into the middle, and that's just off. So this is pretty cool for control because you can be like, that's forward, that's reverse, and then in the middle is stop. So it's very ergonomic. It's a good ergonomic control. It's a lot more ergonomically controllable. I'm not sure if that's correct. It's a lot more ergonomic than this circuit, that's for sure. So this is a good way to do it over here. Now the other way is this. Okay, so this is cool. We can use relays. Now in this case, if we had two relays and two normally open buttons, then we could just press one for forward and press one for reverse, or we could put toggle switches in here. That's good. You can put a toggle switch in there, so you can put a single pole, single throw switch in there. No problem. You can put two of them, one or the other, or whatever you want. You can put a limit switch in there, whatever you want. You can control this. You could also do the same with these. Anyway, let's just go over here. So you've got the options of actually driving relays and then using the contacts for the relays to connect to the motor like this. So let's unpack this. If I were to close this, this energizes, so therefore this becomes closed, this becomes closed, this is open because I have not energized that relay. This is open because it's not energized, so the current goes straight through the motor this way. Okay, that's fine. Now, if I release that button, and I close this button, then this is open, that's open. This becomes closed, that becomes closed. Watch this, the current goes here, it goes through the motor this way, polarity flip, sweet, and then it goes this way and back there. So I've just controlled the motor. Yeah, so in both directions. Now, there is a problem. Wait. There's a problem with this. Actually, there's a problem with all of these, actually. There are two problems with all of these, but some of them only have one problem. I'll just continue. There are two problems here. One is that I can short this out. There are three problems. One is I can short it out. The other is that I can actually short both of them out. So I can tell the motor to go forward and reverse at the same time. Plus, I can switch it really quickly. In this case, I could turn 1 and 3 on, and then I could open them and really quickly change 2 and 4. And the motor's spinning this way, and all of a sudden it's like, well, you want me to spin the other way? Excuse me, I'm driving a load. I'm working really hard, and all of a sudden you've given me direction. Hey, spin the other way. That's not good for a motor. It's not happy about that. You gotta let it stop and like chill out for a second before you put it in reverse. I mean, you can't just throw your car in reverse while you're going on the highway. Okay, good. So in this situation, you can do that as well. You can do a flip back and forth quickly and mess your motor up. But if you look here, there's no way to turn both forward and reverse on at the same time. You can't unless you toggle it really quickly, back and forth. It's really confusing for your motor, but you wouldn't do that. Same thing with here. So the only problem with this circuit is you can switch the polarity really quickly. It's a problem. Here, same thing. I can put forward and reverse at the same time. That's not good, right? You'll short out your circuit if you did that. If you press forward and reverse at the same time, this would become closed, this would become closed, and the current wouldn't even go through the motor. It would just go bam right through here and kill your contacts. So this is a problem here. It's not good. So also you can do forward, let go, hit reverse really quick, back and forth, back and forth. Okay, there is a way to deal with this, and it's called a safety interlock. Safety interlocks are really important. Safety is actually really important, but safety interlocks are things that we put in a lot of control systems. You have to think about safety interlocks with a lot of things. Like for instance, in a milling machine, in a CNC machine where it's going automatically, dude, the machine will not start unless the door is closed. You've seen that kind of thing before. Some cars, you can't start, if you're driving a standard, you can't start the car unless your foot's on the clutch. Or you can't put it in gear unless your foot's on the brake. So you know those are safety interlocks. So we can put a safety interlock here, and this is really cool. Watch this. If I press this button only, everything's going to work. But if while I'm pressing forward, I hit reverse, look what happens. That becomes open. And it turns off forward. Actually, and then because forward's turned off, this becomes closed, and all of a sudden it just goes in reverse. Well, if it starts to go in reverse, no, that's not actually going to happen either, because I have my finger on the forward button. Yeah, it's not going to work. Doesn't matter what, no matter how you look at it, the motor's not going to work. If you press both of the buttons at the same time, the motor's just going to be like, no, right? Because both of these are going to be open. No matter how you look at it, if I have this and this, the relays are going to actually fluctuate a little bit. They'll be like bang, 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 bang and forth. So, but no matter what, it's not going to turn the motor on. That's good. Now, the three problems we discussed was shorts. We can see that there was a short here. We don't have that problem with the safety interlock. We can also see that, yeah, if you try and get the motors to do both forward and reverse at the same time, the circuit shorts. We've seen that. Okay, so that's one big problem. The other problem is the quick, like this, and then let go and then hit the other one really quickly. Guess what? We can't solve that problem right now because we haven't studied motor encoders. Yeah, if this quick switch thing, hit one and then quick hit the other one, back and forth, we can't deal with that with the components and with the stuff that we've studied so far. What we need is a motor encoder, and then we need actually a more complicated circuit to take the very, very low voltage signal, extremely low voltage signal from my motor encoder and put it into my logic to say, hey, you know what, maybe it's going to open a relay contact to say, no, dude, you cannot turn the reverse on, say it's going forward, and you let go, and it's still spinning. That motor encoder, which is just a sensor, it tells you the motor's spinning, and then finally it stops spinning, and then boom, it stopped. Now the motor encoder, the signal from the motor encoder says, hey, you know what, the motor stopped. You go ahead, and you can hit the reverse now. That's a complicated circuit, and we don't know how to do that just yet, and that's fine. You'll study that in Mech 2 and 3, that kind of type of circuitry, and you'll be able to build something like that. Okay, so let's continue on to take a look at the different circuits, okay, and we're going to do a fuse selection. So we're going to take a look at how we select a fuse, which is pretty simple, but let's put a fuse in your circuit, and we're going to look at some designs. Okay, here we go. Fuse selection, this is really simple. What you do is you just, essentially what's going on is that I need to select a fuse for that motor at full power, period, that's it. Unless I'm going to overpower it. Actually, if I did, that would be full power. Again, the power of the motor is not what you read on the thing. The power of the motor has to do with the load. If I know my motor is going to run on 12 amps, I don't want a 12 amp fuse. If I do, it's just going to blow. I want to select a fuse that's about in between 15 and 35. Not over 35 and not below 15% over. So that's a 15 amp fuse. Well, if I just do the math, okay, well let's just do this. 12 times 1.35, that's a 16.2. So if I actually had a 16.2 amp fuse, I could use that. It's okay. If I had like a 17 amp fuse, I wouldn't use it. 15 amp fuse, it's perfect. It works really well because 12 times 1.15, which is 15% over, is 13.8. So 15 amp fuse is just right in the middle, in between 15% over and 35% over. So it's good. So choose a 15 amp fuse and then label your fuse, and then you're good. Now, let's take a look at some of the circuit configurations. Now, if you've noticed here, I've written in green to label everything. And whenever you draw a circuit and you're going to hand it over to someone else to build that circuit, you have to label it. So in a preliminary design, don't label the circuit, label the values, I guess, but you're not going to go and choose the motor components just yet. So don't worry about just label the resistances and the power and the voltage and stuff. But as far as like component, like the manufacturer's code for that component, you don't know what it is yet. You're going to go choose it later, right? So just go with this. But this is your inline resistance power control, PWM, power width modulation. We don't have circuits for that specifically. It's solid state electronics. Anyway, here we go. So here's another concept here where I've got this. We saw this in the PowerPoint. I've just added a fuse because fuses are pretty important. And oh, there's a fuse here too. Oh yeah, fuses are important. There's a fuse here. And then I've just labeled my components and stuff. And by the way, I'm just kind of making a note, just a reminder that these, because of this mechanical connection, this is one switch. You go just go and buy it. It's not actually two switches. Okay, so that's what's going on there. And this is just another way. Again, this is just the reverse circuit, and that's the power circuit. We have to kind of like put them together for our whole circuit to control this in both power and direction. But you can put them together. You figure it out how to do it. This is another way. In this case, we've got our double pole, triple throw. Again, I've got a fuse in here, and you know that's good. Draw your circuit, label everything. Looks like all of these green things indicate that labeling things is actually maybe really important. Yeah, okay, let's go on. So, and this is our ladder logic. Now, if you see here, I've put a fuse in here. And that's acceptable. It's completely acceptable behavior to add things into ladder logic like this. So always put your fuse in here when you're actually building a circuit. If you've designed a circuit and you've calculated a fuse, stick it in here. Maybe your first step of design, you don't put the fuse in. Maybe stage 2 or stage 3. Or at some point, you're going to be like, okay, I better choose a fuse. So this is pretty simple, like circuit control. So you can calculate the fuse pretty much in the first run. Okay, so put your fuse in. There you go. Now, if you are doing a ladder logic for your design, because by the way, for your assignment, you can choose this. You're going to have to choose this because it's the only option. You can put this in however you want, but you're going to have to choose either this type of control, or relay control. If you do relay control, I would like to see interlock, an safety interlock. A safety interlock, yeah. So, yeah, put that in because it's important, because it's safety. And then over here, there's kind of the addition of saying, okay, so now what I'm going to do is I'm going to integrate the speed control, or the power control, pardon me, which also controls the speed, which is a whole other story. So we're going to control the power, and also you're going to control the motor direction with this, but put your safety lock in here as well. So now you're just an expert at motor control. You fully understand that the power of a motor is not just like, you pull it off the shelf. It's a 100-watt motor. Let's turn it on and we'll have 100 watts of power. No, it's not what's going on. It's all dependent on so many different factors. And we can see that the controlling of the power is not a linear relationship. And there are a couple different ways to do it. And pulse width modulation is the most common, although we're not dealing with integrated circuits. So the only option that we have here is actually to dial this in, is to put an inline resistor. We could also put something called a rheostat in here, which is really cool. But essentially, it's just an adjustable resistor. It's actually just a potentiometer hooked up kind of in a cool way. So, or we can have different resistors. Now, generally, potentiometers aren't able to handle the current and the load and the power, because essentially, you know that the reason this motor, where's the motor? The reason this motor here is, the motor's down here, is running under power is because the resistors are stealing a lot of the energy. That means they have to produce a lot of heat because it's a powerful motor. So potentiometers can't do that, or more specifically rheostats can't do that. So we don't really use rheostats to control anything that's really powerful and over like a couple watts. Here you go, or else it would have to be a really big rheostat. So we just use a bunch of different resistors. And by the way, the speed, the fan in your car, or in a car that is controlled, the fan speed, yeah, it's exactly like this. This is exactly how it works. And the resistors that are actually under the hood there, they're big. They're actually coiled resistors. Yeah, because they actually have to produce a lot of power, because the motor in your car that's controlling the fan is actually really powerful. Like, it's probably a couple hundred watts. There you go. So I think you're an expert at this now, and you're good to go to do calculations for your assignment, and you'll be an expert at it, and I'm looking forward to your work. Okay, bye.